All right, so let's go ahead and talk about blood pressure. Blood pressure, we gotta define it, right? Talk about how we calculate it and then get into vasoconstriction and how we can use that to adjust blood pressure. We'll talk about different mechanisms for regulating blood pressure and how we measure it, and then talk about pulse pressure and mean arterial pressure, or MAP, and how we can calculate that as well. I know you're probably thinking, why is there so much math in this particular unit? But again, a lot of this is coming down to numbers of how can we measure somebody's health. Basically, we want some numbers that can tell us how well somebody's heart is performing and how well somebody is able to move things like oxygen and whatever around the bloodstream. So what is blood pressure? Right, blood pressure is the force exerted, right, or generated by a fluid pressure, right, pushed by the blood onto the walls of a blood vessel. Basically what that means, right, if you think about it, you fill up a water balloon with water. That water inside the water balloon is pushing out on the plastic balloon walls, right? Your blood is doing the same thing, but inside your blood vessels. And so we can calculate blood pressure, right, because that doesn't really tell us a number, right, that concept, but we can calculate that number. We can calculate the pressure or look at what affects blood pressure by looking at how much blood volume you have, right? The more volume you have, the more pressure, right? If you put more water in a water balloon, it's going to feel tighter, right? That water is going to push out on the plastic more versus if it is less filled, right? You have less water in the balloon, right? Less pressure being exerted. Stroke volume, right? How much blood is being ejected by the ventricles. Total peripheral resistance and cardiac rate. We'll talk about this a little bit more, but if we increase these, we get an increase in blood pressure. And then of course, if we go through vasoconstriction, then this raises blood pressure as well, right? Higher than where the arterioles are at. Vasoconstriction meaning we are constricting, we're making those arterioles smaller, which means less space for blood to flow through, which means higher pressure, right, ahead of time. So if we look at arterial blood, that's going to be our pressure, cardiac, that's going to be our output, and then peripheral resistance, right? Kind of what we're looking at here. If we're looking at vasoconstriction, right? So here we have, blood, right, or whatever fluid being pumped in, right? If we constrict this, we make this space smaller, right? Downstream, we have less pressure. Upstream, we have increased pressure. And that makes sense. If less is getting through, there's a smaller volume here, which means it's easier for it to flow through with less pressure. Leading up to it, higher pressure. So think about like crowd control. If you have a designated exit and you only allow a certain number of people to leave through that exit at a given time, right? If you do that, on one side, you'll have a lot of people trying to get through the exit. So there's a lot of people building up with high pressure, big crowd, right? But as people are leaving, if you look on the other side where the people leaving are being controlled, you have a smaller crowd, right? It's a smaller crowd because not as many people are allowed through. So same kind of concept as what we see here. So what can regulate blood pressure? So the kidneys can, right? We talked about this just in the last video and a couple times before, where the kidneys help control blood volume, and blood volume is related to blood pressure. The higher the blood volume, the higher the blood pressure, generally speaking. Right? Cortisol, so this is going to be a hormone, right, coming from the adrenal glands. This is going to stimulate vasoconstriction, which is going to increase blood pressure. Baroreceptors, which are going to detect pressure in the aortic arch. We also have the carotid bodies found in the carotid sinuses. They will respond to increased blood pressure. Basically, increased blood pressure will cause more stretching, and then that will basically go communicate, these receptors will go communicate with the medulla in the brain to say, hey, we're under high pressure, we need to lower this pressure, right? And so then the medulla can control things like heart rate and whatnot to lower blood pressure. Venous return, which is stimulated by the sympathetic innervation of the veins. This will basically, if we need to lower blood pressure, we can inhibit ADH, right? So more water in the urine, lower blood volume, lower blood pressure. It also can stimulate the release of the ANH, right? The atrial natriuretic hormone. Because again, more venous return means the atria get stretched more, and if the atria get stretched more, then that will trigger the release of ANH, which means release salt. And as we release salt in the urine, water will be pulled with it, so more water in the urine too, which again leads to lower blood pressure. So we're seeing a strong link now, if you haven't noticed it yet. We're seeing a strong link between the cardiovascular system and the urinary system, that they're kind of tightly tied together in terms of regulation of things like blood pressure. So how do we measure it? So this is measured in the units of millimeters of mercury. Basically just, it's a measurement of pressure, right, is the unit. We use a sphygmomanometer. I have a hard time saying that word, so if you do too, that's okay. But basically we have two numbers when we read blood pressure, because when we are reading blood pressure, especially when we're getting it from like a cuff, right, we are measuring through an artery, which means it's going to fluctuate based on whether or not the ventricles are contracting. So there's always two numbers in a blood pressure reading. So for example, 140 over 90 or 120 over 80, right? Those are both examples of blood pressure readings. The top number is the systolic number. The bottom is the diastolic number. And what we're talking about is with systolic is, are the ventricles contracting, like actively contracting, which will be higher pressure? Diastolic, are the ventricles relaxing, which makes sense that it would be lower pressure. So when we're taking this reading, we have the cuff on, right? We increase the pressure so much so that the artery is basically pinched shut, right? So we apply so much pressure to the cuff that we cannot hear any blood flow through the artery. It's quiet. There's no blood flowing through the artery and it's quiet. As we release the pressure of the cuff, right, the artery is going to open with each systole, so each ventricular contraction. And that's where we get our first sound, right? Because we can hear the blood kind of flowing through there. There's a noise that actually gets produced. We call it the sound of Korotkov. So we get that turbulent flow when the ventricles contract. And we hear it every single time the ventricles contract until finally we get to the very last sound. Right? So we go beyond blood pressure, we close off the artery. The first sound is a systole, right? The second sound when pressure reaches diastolic pressure. Right, now we hear laminar flow, right? That's the last sound, which means we're back to normal. So, and we read the pressure of when we got that last one. And so that's where we get the two numbers and what the two numbers mean, right? The first number generally is higher because we're talking about active ventricular contraction, and diastolic, that number is lower because we're talking about like the ventricle relaxation. The pulse pressure basically tells us a little bit about the stroke volume, and we're just looking at the difference between the systole and the diastole. So if your blood pressure is textbook, meaning it's 120 over 80, we would just minus 80 from the 120, giving us 40, and so that would be the pulse pressure in this case. If we're taking a pulse, we're talking about measuring heart rate, right? And basically we're just looking at that increase in that blood pressure in that artery during the systole. So every time you feel that pulse, you feel that bump, right? That you're feeling the change in pressure. You're feeling that increase in pressure being exerted on that artery every time a ventricle contracts, which is why we can use it to measure heart rate, because the ventricles are going to contract once per cardiac cycle. And so every time we feel that bump, we feel that ventricular contraction, right? At least indirectly. And so every time we feel it, we can say we're feeling one single heartbeat. The mean arterial pressure is the average pressure in the arteries during a cardiac cycle. And this is different because in this case, right, we're taking a little bit more into account. We're looking at the difference between the mean arterial pressure and the venous pressure that drives blood into capillaries. So if we calculate it out, we're going to, if we want mean arterial pressure, we're going to look at the diastolic pressure plus 1/3 of the systolic pressure minus the diastolic pressure. Right, that's what we're calculating there. And so mean arterial pressure is going to be more flatlined, right? So if we're looking at this one here, right, we see we have like, was it 140 over 90 it looks like. So 140 over 90, if we calculate that out, diastolic is going to be 90. We're going to add that to 1/3 times our systolic, which is 140, minus our 90, so that's 50. Right, 1/3 of 50 is approximately like 18-ish, 18 something, somewhere in there. I'm not necessarily using a calculator here. I'm just kind of going off of my head. So it's like 17, 18. And so in this case, right, 107 to 108 roughly is going to be our mean arterial pressure. And if we look at this here, like we see it's maybe a little bit lower. I may have miscalculated the 1/3 of 50. But still, it's pretty dang close. It's probably 16. Even then, we're close to what I got just by doing a quick math, right? And if we look at the picture here again, we see, bam, we're somewhere around there. Again, I was just estimating the 140 and the 90 there.